Okay, so let us start this afternoon session with the last talk of the day and of the week by Julien Randon-Furling from Paris. We talk about first-passage resetting.
Yeah, well, depending on the time, because with the temperature, I don't want to keep you 2 hours, so maybe it will be just 1 hour first passage problem. So first, thanks to the organizers, particularly Filippo, for this great workshop and for the invitation. So yeah, as I said, that's a long list, but probably we won't go through everything. The topics are maybe slightly different from what you've heard so far, at least from what I've heard. I'll talk mainly, well, exclusively about Brownian motion and mostly about first passage resetting. So I don't know if any of you is familiar with that, but you'll see that it's very simple. And the nice thing is that we can compute explicit formula analytically, or sometimes using path transformations. So I'll show you a number of path transformation solutions to some of the problems. And just to state what resetting is, so it's the idea that you have a random process, so think of a random walk or a Brownian motion, and you restart it at some times. So these times can be fixed. That's then a textbook exercise. You can have random times independent of the process. And that's there's quite a huge literature in the last 10 years. This is called stochastic resetting. And you can, for example, have exponentially distributed times when the process is restarted, and it has nice properties, and you can optimize it. You can find an optimal rate of resetting in random search problems, for example. That's very useful. And the type of resetting I'm going to focus on is first passage resetting. So it's a type of resetting in which the random times when the process is restarted actually depend on the process. And well, as the name indicates, they depend on the first passage to a certain level, or when the process first reaches a certain configuration. There's a 1953 paper by Feller who introduces actually this. He calls it instantaneous return or elementary return process. And he proves that the process exists and that it has solutions with unicity under certain conditions. Of course, we were interested in sort of explicit formula for densities and other quantities. So we couldn't find everything we wanted in this paper by Feller and the one by Sherman, who looked at the bounded geometry case. So I'll first take you through a simple case of first passage resetting in a semi-infinite geometry. So imagine you have a Brownian particle that starts at 0. So okay, the drawing is very crude. It's obviously not like a Brownian path, but you can imagine. And when it hits a certain level, say L, when it's restarted, so it's reset at its original position, etc. And we just want to study this process and get things like, PDF for the nth reset time, the position at time t, the number of resets. So if you think of this simple Brownian semi-infinite geometry, then you know that with probability 1, you're going to hit L, but the average time it takes is infinite. So that actually explains the sort of rich phenomenology that we find in this process. Okay, let me start with the first question, which is the PDF of the nth reset. So we could obviously go through some, there's a convolution structure because it's a renewal process. So you can do a Laplace transform, but there's something easier that you can do, and I'll show you on the blackboard, is you can take, well, let me come back to the previous picture. So when the process is reset, you can actually take this second part here between T1 and T2 and shift it upward to level L. And then you do the same thing with the next part. You shift it to level 2L, etc. And what you get is just a Brownian path with no constraint. So you can actually immediately see from this path transformation that the time of the nth reset is going to be just the first passage time of a standard Brownian motion at level NL. So obviously you retrieve this using the convolution structure and the Laplace transform, but you can see it immediately using the path transformation, and you get the PDF for this. And then if you want to look at the PDF for the position, so you're asking what's the probability to be at x, or in xx plus dx at time t, Again, you can use the convolution structure, give as a forward or a backward renewal equation. The backward one is slightly easier to handle. But you can also, again, make use of this path transformation and see, for example, if you get here and then you want to know what's the probability that you end up, let's say, somewhere at some position X here, then you see in that case, you can say if X is less than L, which is the case, if I come back to this picture, which is not the case on this picture, but imagine if you have a positive X, which is between 0 and L, then this is going to be equivalent to finishing at some X between NL and N plus 1 L, under the condition that you haven't crossed N plus 1 L. Okay, so that's if you have a positive X. So you can actually use this path transformation and immediately get this result, which is for X between 0 and L. And you can see it in the solution. That's really just the superposition of going directly from 0 to NL plus X, which is what I said here, and using the good old image method. You subtract the paths that come from the image in N plus 1L. So you subtract X with the paths that come from N plus 2L. And you sum over all N, because then it's just the number of resets. And you can get this immediately. There's a long time limit, which is nice because it's just linear, as you could expect, because basically between 0 and L, what happens is that the flux exiting at L is just re-injected at 0, and then you get this shape. Now you want to know what happens for X, or at least I want to know what happens for X negative, so this case. So if you think about the path transformation, if X is negative, then you end up somewhere here. And this is not as nice as before, because you have to impose a condition, okay, that you haven't crossed N plus 1L, but you reach X, which is lower than NL, and you want to impose the condition that you've crossed NL. So that signals that it's actually not the right path transformation to use. I'll show you a better path transformation for this, but before that, I'll show you the solution using the Laplace transform, which is actually very easy. And if you don't think about the path transformation that I'm going to show you now, you can actually read it from here, because you see that the analytical solution is just a superposition of paths coming from 0 and paths coming from L. And in fact, the path transformation behind this is reasonably easy. So if you are in this situation, so you reach X with here 1, 2, 3, so an odd number of resets. In that case, what you're going to do is that you will symmetrize. So you take this blue part, so you symmetrize the odd numbered parts of the path. So you just flip them, and so flipping this one, it will become this one. And you do the same thing for the green one, and it becomes this one. And what you get is a path, Brownian path that starts at L, finishes at X, and it has no constraint. And if you have an even number of resets, you do the same thing with the even numbered parts of your path. And what you get is a path that starts at 0, finishes at X, and has no constraint. So you exactly get the superposition of these two things here. So you can either use the Laplace transform or think about the path transformation. And I usually like to try and find path transformations, just because I'm lazy and I don't want to do calculations. That's when you find it. Well, sometimes you think a long time for the path transformation, but then you don't have to do the calculations. In that case, the calculations are simple. So, but in the things I'll show you later on, they're not so simple. You can also compute, still using the renewal equation. You can compute the average number of reset events, of resets, so that grows like square root of t, which is not very surprising. And let me now show you something we can do with this first passage resetting, which is an optimization problem, defining an optimization problem. The idea is simple. You imagine that you have a system, could be a mechanical system or a financial system or whatever, and you model the operating point of the system by a Brownian motion, x of t, with a diffusion constant d. And now it's going to be bound, this value between 0 and L. And you imagine that L is the sort of maximum operating point of your system. And if it reaches L, it breaks down. And it costs you some money to repair it, for example. And at the same time, you want the system to operate near its full capacity because it's more efficient, for example. And you can control your system via some mechanism that is modeled by a drift V. So you can either push your system towards its breaking point or refrain it from reaching it. And basically, we just want to maximize this objective function, which is the average position, and you want it to be as close to L as possible. And it's penalized by the number of breakdowns with the cost of breakdowns. So in that case, we can reformulate the problem in terms of convection diffusion equation with still re-injecting at 0 the flux that lives at L, because when the system reaches L, when it's restarted at 0, you have these initial and boundary conditions. And now we're in a bounded geometry, so it has actually a steady state solution, which can be expressed exclusively, well, in terms of L, obviously, but also in terms of the so-called Peclet number, which is basically the rate of the drift so that you can see it as the sort of convection rate divided by the diffusion rate. So it measures how strong the drift is compared to the diffusion in your system. And then also, again, using the renewal structure of the problem, we can compute the first moment, which we're going to use in the objective function, and the average number of resets for the time t. All of these in terms of LT and the Peclet number. So we can write our objective function like this, and then we can just plot it in terms of PE and this C over L squared over D, which is C prime. So it's basically the cost, normalized cost. And you can see that there is, in fact, always an optimal Peclet number. So it's an optimal drift at which you should drive the system if you want to optimize this function. And, as you might expect, if C is small, it means that when the system breaks down, it doesn't cost you too much. So it's actually worth it to push the system to have a positive Peclet number. So you're actually pushing it towards its limit because it's not too expensive when it breaks down. And if C starts to be relatively high, then of course you're going to have a negative Peclet number, so negative drift, because you don't want to push the system towards its limit. Okay, so that's one type of things we can do with first passage resetting. There are many, many variations around this. You can introduce a delay for repairs, not just a cost, let's say. And that's actually, with Brownian motion, you can relate this to problems that are sometimes referred to as sticky Brownian motion. So you can have your particles that sticks either to the upper boundary or to the lower one before it is allowed to restart. So we've treated this case, actually. You can let the boundary move every time you hit it. And you have some interesting boundary recession phenomena. You can look at higher dimensional cases, which Sherman did in his 57 paper from slightly different perspective, but he did it there. You can reset at a random point. Or you can do also multi-particle resetting, which is a bit like higher dimensional, but let me show you an example of this. Which we devised having in mind a sort of very simplistic story, imagining that you have n agents in a society and you model their wealth by the evolution of their wealth by Brownian motion for each of them. And this system of n agents, they can follow one of two rules. Either they're so-called altruistic, and if one of them goes bankrupt, then they share the remaining amount of money between all of them. So they save the guy who went bankrupt, and they all restart with the average that was in the system. Or they behave egoistically, and they just let the poor guy go bankrupt, and the other ones continue their lives. And so that can be formulated in terms of resetting. So, for example, with two particles, so you start here, they both have initially X naught money, each of them, and they start here. And for example, at the first event is this one, and it means that X1, so guy number 1, went bankrupt. And if they share what guy number 2 had, then the particle is going to be restarted here on the diagonal, and so on. And then you say that the system is bankrupt or dead when they reach, for example, a small region here with upside and upside. In fact, so you want to compare this to the same thing, but with individualistic features. That is, you know, when one hits 0, then the other one just goes on in its life. So in that case, that would mean, you know, this the two-dimensional particle gets here, and then it does a Brownian motion just one-dimensional on the axis. So that's the individualistic system. And to compare the two, you can use order statistics for the individualistic system. So you can compute, you know, the distributions for the last remaining individualists in the system. And for the altruistic, or so-called altruistic system, actually you just look at the average, empirical average of the wealth in the altruistic system, and this follows a Brownian motion, which with a diffusion constant that's just rescaled by the number of particles. And so with that, you can basically compute everything. So what we computed was the survival probability in both cases, and well, for altruistics and individualists, and also the median wealth. So the median, we computed it numerically in the sense we got the expression, the exact expression analytically, and then said, okay, we look for the median by saying that the integral should be equal to 1/2, and then you get the median. So if you look at the survival probability with 2 agents, so you see that the altruists actually do better than, of course, the first individualist that dies, but not as well as the second individualist that dies. And in terms of median or typical wealth of agents, it's nice to see that, because you see that, okay, then basically in the individualistic system, what happens is that you have one guy that goes bankrupt fairly quickly and is worse off than the altruists. But then the survival individualists will actually be better off and for a longer time, as we've seen before, than the altruists. And then if you move to a larger number of agents, for example, 16, you observe the same thing, and you look at the last 2 surviving individualists, then you have again that typically the survival probability of the one before last, the penultimate, is eventually less than that of the altruists, but the last remaining individualists will have a larger survival probability, and you have the same thing as before for the mean wealth, or median wealth, sorry, in the system. And so then we discuss in the paper, but I won't discuss it maybe here. You can, of course, look at this in terms of strategy, and then look at expectations, or what can an agent expect initially if you allow them to change strategy or not during the evolution. And the interesting thing is, of course, if you're not allowed to change strategy, then the altruistic strategy is better. But if you're allowed to change strategy, if you're not the first among the first individuals or among the first people to go bankrupt, of course, you might say, well, actually, we did agree that we would be altruistic, but since you died first or you went bankrupt first, we're not going to be altruistic, and then you're going to be better off. So you can look at this from a sort of game theory perspective. Right. So let me now come to another problem, which does not involve resetting, but does involve Firstpassage. It's inspired by a foraging problem that was suggested to me by Paul Krapowski, and it's a very straightforward model. So you imagine you have an animal that's foraging. So it's a one-dimensional animal in a one-dimensional world. It's foraging on this line, and you model its position by Brownian motion. And there's 1 unit of food per unit length. There's no food replenishment. The animal can stockpile whatever it eats, and it needs 1 unit of food per unit time to survive. And the question is, what is the survival probability? What's the probability that it survives up to time t? To make things simpler, we started by thinking about there's food on one side only. So you have this animal that lives on the verge of a desert, basically on the brink of a desert, and there's food just on one side. And in that case, you realize that if you look at the supremum of your Brownian process, of your Brownian motion, then the supremum is the running maximum is the space that you've explored on the line, on the side on which there is food. So it's equal to the amount of food that the animal has eaten and stockpiled. And therefore, the survival probability is just going to be the probability it survives until time t is just the probability that the maximum remains above the diagonal. So the running maximum is should always be larger than the elapsed time up to time t. So that's the thing we want to compute is this. So it's basically a first passage problem for the Brownian maximum. I'm sure many of you already think of many different ways of tackling this problem, and there are, and I'll tell you about them later on, but let me show you one solution that again uses path transformation. So the first idea is that we want to, well, sort of a la physicist approach is to think about the paths that have that die at time t. They die because m of t is equal to t. Okay, so the maximum is equal to the time elapsed, so you're dying. But of course, it could happen. It doesn't mean that when you have m of t equals to t, it doesn't mean that the path dies at time t, because it could have died before. Okay, it could have been that there was a time before when the max was already less than the elapsed time. So if you look at this example, okay, this has m of t is equal to t, if this is t, but for example, it already died here, and even if it hadn't died here, it would have died here and already here, etc. So obviously, it's a little bit more complicated than just computing the PDF path to have a max equals at t at time t. But you can think about this approach and think, okay, I'm going to consider these paths that have m of t equals t, but what I want to do is to subtract from these paths the sort of probability weight associated with the paths that have m of t equals t, but they died before. So this is very sketchy, obviously, because, okay, this is probability 0, it should really write it rigorously, but that's the idea behind it. And so of course, this we know. So the challenge is just to compute this. And it is this part that I will now show you how to compute with a path transformation. So imagine you have a path that has m of t equals t, but it has for some time s. So for example, here, so there's a time s here where m of s was equal to s. So the max is equal to s, and that's the time s here. Then I'm going to be interested in these two times. One of them is tau 0, which is the first time when s was reached. So that's the time when this maximum was set. And delta is the first time that s is hit after s. So s I should have written somewhere here. It's when the red line crosses the diagonal here. And you know that, well, you know that t naught exists because m of s is equal to s, and you know that delta exists because m of t is equal to t, and is strictly larger than s. So these two terms are well defined. Yeah, I have to say, when you do path transformations, I skipped some of the details, but you have to be very careful, of course, about the existence of the times at which you want to cut the path. And you also have to be careful about the way the Brownian motion arrives in a point. If it's like a first passage point, then if you transform this part of the path, it means that whatever you do with this part of the path, it has this structure that it is either entering or leaving a point in a very special way. So you always have to pay attention to this. Okay, so I have these two times, and what I'm going to do, just to give you heuristics, is I'm going to use, so you see here, you have a downward excursion, which is below level S. So in some sense, it's useless in the path. It's useless for the path to reach t. You know, you could take this downward excursion out, just move this forward in time, and you would still have a path that has a maximum equal to t. So you can take this out and do whatever you want with it to change the path, and that's what I'm going to do. So yeah, that's what I said. We're going to extract it, and we're going to use it to create a path that has basically will have a maximum that is higher than t. And then we'll show that everything works well. And in the end, the subset of paths we're interested in will just be in bijection with the set of Brownian paths that have a maximum larger than t, and this is very easy to compute. So let me show you the way it works. So we'll need another time, which is tau star, which is the time at which the maximum, global maximum, so here t is attained. So we have these 4 parts now. Well, we have the part up to t tau naught, which I'm not going to change. Then we have the blue part, which is between tau naught and s. The sort of orange part between S and delta, a short green part between delta and tau star, and then this yellow part, which is the final one between tau star and t. And let's see if normally there's an animation. I hope it works. So what I'm going to do is use the blue and orange part. So I'm splitting the excursion not in the middle, but at the time given by S. And then I'm transforming the excursion in what is called a first passage path. So you turn around one of the parts, the 2 parts of the excursion, and you get a first passage path. The rigorous definition of this path transformation is in just this specific part of the path transformation is in a paper by Bertoin in the early 90s. And so you can use this to produce a first passage path that you will use to basically boost your maximum and put it upward larger than t. So it gives something like this. So you see, you take the so the green part that is here, you move it forward in time there, and then with the blue and orange part, you instead of having an excursion, you produce this first passage path upward, and therefore it sends your maximum, global maximum, to some level which is higher than t. And I haven't shown it here, but in fact, you can keep track of the, so let me try and stop it at a nice time. You can keep track of the amount by which your maximum is going to be shifted upward, because it's exactly, so this time here, when the excursion is split, this time is S. So if you look at S minus BS, B of S, it's exactly twice this value is exactly the amount by which the maximum is going to be shifted. So you can keep track of this, and I'll mention it later again because that's useful. Okay, let me see if it works. Okay, so it's stuck on the animation. No, maybe not. Okay, so we obtain a global path, a path which has a global maximum larger than t. Of course, maybe I still have a bit of time. So you have to check that it's a bijection, so you have to check that you can transform back into a path from the original subset. I won't give you all the details of it, but we can do it, and it's in the paper anyway. So in any case, what we managed to prove is that these paths, which have m of t equals t and m of s is s for some s less than t, they're actually just in bijection with the set of paths that have m of t larger than t. And this now that's something we know, we can just use the PDF for the max and integrate it from t to plus infinity. And you get this, which is the PDF for the time when the animal dies, basically, or for the first passage time of the maximum at the diagonal. So as I said, there are other ways to obtain this result. One of them is to look at the reciprocal process of m of s minus s. And this is a spectrally positive Levy process, and you can use the machinery associated with that to derive the time. And that's done by a paper by Dooney in 91. And another nice way of doing it is to directly show that the first passage time at 0 of m of t minus t, so it's a bit like an arcsine law, is distributed like the sojourn time above 0 of bt minus t. And this is done in a paper by Imhoff, 1996. And so you can use that and you find this result. The thing you do not find using these approaches is the joint distribution, which I haven't shown here, but I've mentioned it. With the path transformation that we've devised, you can actually have the joint distribution of this time and the position of the Brownian walker at this time. And you cannot get it with, or at least with these approaches, the way these approaches were devised here. Yeah, I still have like 5 minutes at least to mention that. So now if you come back to the original problem with the food on both sides, and actually I won't even need 5 minutes because you see that the problem is going to be a problem for the range, and it's going to be a question of first passage time of the range below the diagonal. And so if you look at the range, that's the max minus the min. And of course, it's more difficult to characterize. So it's not going to be like just looking at the max and wondering when it does go below the diagonal. You can think about some characterization, of course, if the max is less than t by 2 and the min is more than minus t by 2, of course, and you know that the path is already dead, etc. But apart from that, there's no very simple characterization. So this is actually, well, you can try and think about something similar, but we haven't managed so far. So this is still an open problem. And, we're working on it with Paavo Salminen, Pierre Valois, and Paul Krapivsky. And well, if you have any idea, we're actually very happy to hear about that. So I think I'll finish here. And so many thanks again for the invitation, Filippo, and many thanks for your attention. And if you have questions, we can use time.
Thank you very much. Actually, you had more time, you know.
Yeah.
So, any question? I have one question, but right at the beginning, there was you showed this sum of two reflected from origin starting from L.
Yeah, let me get back to that.
I was wondering if search result can be updated with some kind of image.
Yeah. Well, there's this one, which was for X between, so when, no, let me come back to, yeah, this one. So when X is between 0 and L, it's really just a superposition of image methods, because when you do the path transformation that is on the blackboard, okay, yeah, it's just, going to NL plus X and, but not crossing N plus 1 L. So this is really just the image method for each level NL. The other one, I don't know, I could only think about the path transformation that I showed you, which is this one, which is not like the image method, but in some sense, many path transformations that are devised to get PDF for position are in spirit close to the image method, or to, as I showed here, sort of cutting and stitching pieces of a path. This one, no, not in the first part, no. In the second part, when we do the optimization, it is, because we force it to be between 0 and L. But in the first part, it's not bounded below. Yeah, we didn't think about that, but yeah, you could. Yeah, you could. We could look at something like that. Yeah.
Other questions? If not, thank you, Gabe.